In the first revision lecture in Unit 2, we're going to look at homologous series. So what do we mean by the term homologous series? Well, all the members of a homologous series must have the same general formula and they must have similar chemical properties. In this section we're going to look at three homologous series: alkanes, cycloalkanes and alkenes. So alkanes have all members of the alkanes have the general formula CnH2n plus 2. Cycloalkanes all have the general formula CnH2n, and all members of the alkenes have the general formula CnH2n. So it's perfectly obvious from that why alkanes are a different homologous series from cycloalkanes and alkenes. But why are cycloalkanes and alkenes not in the same homologous series? Because they have the same general formula. And that's because they don't fulfill the second criteria. They don't have similar chemical properties. All alkenes are very quick to undergo addition reactions. Which is one of their main identifying features, whereas cycloalkanes do not undergo addition reactions. So although they have the same general formula, they don't have similar chemical properties. So you must have these two things to be in a homologous series. So let's look at the first homologous series, alkanes, in a wee bit more detail. Well, the first member of the alkanes, the simplest alkane, contains one carbon, and every carbon always forms 4 bonds, and that's methane. The next member contains 2 carbons, and the simpler alkanes are just increasingly longer chains of carbon atoms. So the next member has got 3. And you notice that each carbon atom has got 2 hydrogens on it, which where the CnH2n comes from. But in addition, the end carbons, the 2 end carbons also have an extra hydrogen, which is where the +2 comes from. So this is methane, ethane, propane. But you don't have to remember all the names of the alkanes. They're given to you in the data booklet. So in the data book it lists the first 8 alkanes in order of increasing number of carbons: 1, 2, 3, 4, 5, 6, 7, then octane 8. So you can always look up your data book to find the names of these alkanes. While we're here, it's worth noting that in all homologous series, melting points and boiling points increase from the small molecules to the big molecules. So like methane boils at -164, octane at 126. So within a homologous series, bigger molecules always have higher melting boiling points than the small molecules. Right, it's important to know the difference between a molecular formula and a structural formula. So for example, for ethane, molecular formula just tells you the number of carbons and hydrogens, C2H6. But the structural formula actually shows all the bonds and shows how these 8 atoms are all joined together. We'll normally use full structural formula, but sometimes we use shortened structural formula, which I don't find it so useful. So for ethane it's CH3, CH3, just saying that carbon's got 3 hydrogens, then that carbon's got 3 hydrogens. And butane, molecular formula, just tells you how many carbons and hydrogens. Here's a full structural formula, and here's a shortened structural formula for butane. CH3, that's that one, CH2, CH2, CH3. Right. As well as the straight chain alkanes, you also get alkanes which are branched. So here's the example of a branched alkane. In total it's got 7 carbons, but it's not simply heptane, because heptane would be 7 carbons just joined in a straight chain. So how we name it, we look for the longest chain of carbon atoms. So that would be those 6 along there. Then we've got a branch, which is just a 1 carbon branch, which we say is methyl. Then we have to say where the methyl group is. If we number from this side, we get 1, 2, 3, 4. If we number from this side, we get 1, 2, 3. So we'll always number from the side, which gives us the smallest number for the branch. So this would be 3 methyl hexane. Oh, in this example we've got 2 branches. Here's our main chain of carbon atoms, 1, 2, 3, 4, 5, 6 again, so that's hexane. We've got a methyl branch here and an ethyl branch here because it contains 2 carbons. To get the smallest numbers, we number from this side, so it's 1, 2 and 3. But when it comes to naming it, you always name the ethyl first. You just do it in alphabetical order, and ethyl comes before methyl in alphabetical order. So that would be 3 ethyl, 2 methyl hexane. Okay. And when you're writing it out, you put hyphens in between numbers and letters. Here's one more example where we've got 2 branches. So the longest chain is 4 carbons, 2 branches, both methyl groups on the 2nd and 3rd carbon. So the name of this would be 2,3 dimethyl, because there's 2 methyl groups, and the main chain is butane. So 2,3 dimethyl butane. So here's another 2 branched alkanes. The left hand one is 2,2 dimethyl propane. So even though both methyl branches are on the same carbon, you still have to specify both numbers, 2,2 dimethyl propane. Whereas this is 2 methyl, 1, 2, 3 butane. But the interesting thing in this case is if you write out the molecular formula for this is carbon 1, 2, 3, 4, 5, C5H12. And the molecular formula for this is C5H12. They both have the same molecular formula. So this is one of the limitations of molecular formula. If you know you've got C5H12, you don't know if you've got this molecule or this molecule. So structural formula are far more useful. Now, we call these molecules isomers because they have the same molecular formula but a different structural formula. We come across them quite a lot in this unit. So isomers, compounds with the same molecular formula but a different structural formula. Okay. So moving on now to cycloalkanes. Different general formula, CnH2n. So it's got 2 hydrogens less than the alkanes. So here's an alkane, propane, but to turn it into a cycloalkane, we have to remove 2 of the hydrogens to allow the carbons to join together to make cyclopropane. Okay. So you lose 2 hydrogens. So instead of being CnH2n plus 2, it's just CnH2n. So here's the structural formula for the simplest cycloalkane. You can't make a ring of carbon atoms with 1 carbon or 2 carbons. 3 is the smallest before you can make a ring. So cyclopropane is the first member of the cycloalkanes. Thereafter you get cyclobutane, cyclopentane, etc. But that's the first member. Alkenes also CnH2n. But as you can see from the structural formula, they do not have a ring of carbon atoms. They've got a carbon-carbon double bond. That's what makes the alkenes so unique. So again, going from an alkane to alkene, you have to lose 2 hydrogens in order to make this carbon-carbon double bond. So the first member of the alkenes is ethene, because you can't have a carbon-carbon double bond with just 1 carbon, so there's no such thing as methene. Then you've got propene. And with ethene and propene, there's no choice about where you put the carbon-carbon double bond. There's only 2 carbons there, and it doesn't matter if you put a double bond there or there, it's just the same molecule. However, once you get to 4 carbons, you do get a choice of where to put the double bond. So here we've got but-1-ene, and here we've got but-2-ene. So the number refers to position of the carbon-carbon double bond, and the numbering system is we just number the carbon-carbon bonds. So we call this the first carbon-carbon bond, this would be the second, this would be the third. So it's but-1-ene. Whereas here, there's the first carbon-carbon bond, there's the second, there's the third. So it's but-2-ene. Note, do not number the carbon-hydrogen bonds. So when you're numbering the position of the carbon-carbon double bond, it's just carbon-carbon bonds that you number. And again, they're isomers of each other. Okay, then let's look at this important concept of whether or not a hydrocarbon is saturated or unsaturated. That's an alkane, it's saturated. Cycloalkane, also saturated. An alkene, unsaturated. So what makes it unsaturated? It's having that carbon-carbon double bond. So if we say a hydrocarbon is unsaturated, we mean it contains carbon-carbon double bonds. Not a carbon-oxygen double bond, which we'll see later on, but a carbon-carbon double bond. And there's a simple chemical test to tell whether or not a hydrocarbon is unsaturated, and that is that the unsaturated molecules decolorize bromine water quickly. Let me just demonstrate that. So here I've got it's an unsaturated hydrocarbon. I'm going to add some bromine water to it. Okay, so there's the hydrocarbon and there's the bromine water. They don't mix together very well because the organic and the aqueous bromine water don't mix together. So I have to give it a good shake to get them to mix together. And as you can see, the brown colour of the bromine water has disappeared. It's been decolorized, and that tells us that that hydrocarbon is unsaturated. So let's look at what happens when you're adding bromine to an unsaturated hydrocarbon. What happens is you break one of these bonds in the carbon-carbon double bond. So we've got 3 carbons, but we've only got a single bond there. All the hydrogens remain where they were, but both these carbons have now only got 3 bonds. So it was Br2 we're adding. So we add a bromine atom onto each carbon atom that was involved in the carbon-carbon double bond. And so all the Br2 molecules are used up, and it was the Br2 molecules which had the brown colour, but there's no Br2 molecules left, so it decolorizes it. No, it's not important if you have that bromine pointing down the way or up the way, or in this carbon where it's outside, up top, down the bottom. They're all equivalent positions. So this is an example of an addition reaction. So we're adding bromine to the unsaturated molecule, and it's a very important chemical reaction which alkenes undergo. And although bromine is one we use to test whether or not a solution is unsaturated because of the colour change, there's lots of things we can add to an alkene. So any reaction in which you start off with having a double bond and you end up not having a double bond will be an addition reaction. You can add hydrogen, you can add water, you can add hydrogen chloride. So the double bond disappears, it's an addition reaction. It's a very important class of reactions for alkenes. Right, so where do alkenes come from? Now, most of the molecules that we're talking about in Unit 2 come from crude oil, but you don't actually find alkenes in crude oil. It's mainly alkanes. And you turn the alkanes into alkenes by catalytic cracking. So catalytic cracking is an industrial process for production of smaller, more useful hydrocarbons. So say we have this quite big hydrocarbon, an alkane C12H26, and we crack it. It kind of means we cut it up into smaller molecules. So for example, one of the molecules we produce might be C8H18. The other molecule, well, we had 12 carbons, 8 are there, so we must have another 4 here. We had 26 hydrogens, 18 are here, so that leaves us just 8 hydrogens, which isn't enough to make an alkane. It's C4H8, an alkane would be C4H10. This will be an alkene. So this is how we make alkenes, by catalytic cracking. And alkenes are very, very important because they're the basis of many, many plastics, as we come across later on in Unit 3. Okay, so 5 things you should be able to do by the end of this section. You should be able to explain what is meant by the term homologous series. You should be able to recognise and name members of the alkanes, including branched alkanes, cycloalkanes and alkenes with up to 8 carbons in the longest chain. You don't need to name things beyond 8 carbons. You should be able to recognise isomers. You should know what is meant by the terms saturated and unsaturated, and know how to test for unsaturation. And you should be able to draw a structural formula for hydrocarbons.